We're going to establish a little bit of language for how we talk about matrices. So we're going to consider first this M by N matrix below. Remember that the number of rows always comes first and the number of columns always comes second when we are describing the dimensions of a matrix. So this is M rows, N columns. If we want to refer to an individual entry in this matrix, we can use the lowercase a for the matrix that we denote with a capital A, and we use subscripts for what row and what column we're talking about. And just like with the dimensions of the matrix, we start with the row and then we do the column. So the order here matters. A sub ij is the entry in row I, column j. So we always indicate the row first. Just for a little bit of practice on this, we're going to find B sub 2, 1 in this matrix. That's going to be row 2, column 1. So I can see this is row 2, this is column 1. The intersection of those gets me to this entry right here, and therefore B sub 2, 1 is equal to 5. We also say that two matrices are equal if they have the same dimensions and the same entries in every position. So in this example here, we'd say it's possible for these two matrices to be equal for particular values of x and y. This question really is as simple as it looks. We need to see that, first of all, these are both 3 by 1 matrices. 3 is the number of rows, 1 is the number of columns. So we've got that condition satisfied. Then we look and see that the first entry is already the same. For the second entry, we would need these to be equal, and therefore that tells us that x must equal -7. And for the third entry, we would need these to be equal, so this tells us that y must equal -3. So this definition of equality is every bit as simple as it looks like it would be. The first few operations that we see on matrices are in keeping with this idea of simplicity. In the first example, we're looking at scalar multiplication. Scalar multiplication is different from matrix multiplication because we're not multiplying a matrix by a matrix, we're multiplying a number times a matrix. So in this case, we're multiplying the number 5 by this matrix, and the way it works is kind of similar to what we might think of as the distributive property. It's not the same property, but the same idea that we just go ahead and multiply every single entry in this matrix by the number 5, so the dimensions of the matrix don't change at all. And this just becomes another 3 by 2 matrix that is scaled up by 5. So 7 times 5 gives me 35. Oh, I'm sorry, that's -5. So we're multiplying everything by -5. This becomes -35, then we get a +10 and a -15. And in our bottom row, we get a +5. -5 times 0 is still 0, and +30 as our last entry. Addition and subtraction works if the matrices have the same dimensions. And what you would probably just naturally guess to do is the correct thing to do. We go ahead and add or subtract the entries that are in the same location. So in this case, we have a combination of addition and scalar multiplication. And just like order of operations with numbers, we would do the multiplication first, because multiplication comes before addition in order of operations. So we'll take this 4, which is a scalar multiple of the second matrix, and scale up the whole matrix by 4. And let's rewrite this whole problem now as the first matrix exactly as is, no change. We're still adding the matrices, so I'll keep the plus in here, but I will scale up the second matrix by 4. So this becomes -8, 20, and -4. Now we see that both of these matrices are 3 by 1 matrices, and therefore our result is also going to be a 3 by 1. And the way that I fill it in is quite simply to take the entries that are in the same position and add them together. So 3 plus -8 gives me -5, and that's what I put in the top. Then I get 0 plus 20, which gives me 20. And finally, for the last position, I have 7 plus -4, which gets me +3. So matrix addition and subtraction, very intuitive, exactly what you would probably guess to do even if you weren't told anything at all. We'll just make sure that we start with two matrices that are of the same dimensions and we add the entries that are in the same position. Our result matrix also has the same dimensions. So we had 3 by 1 plus a 3 by 1 gave us a 3 by 1. An interesting application of operations on matrices is digital images. We have a really oversimplified version here of a digital image, very simplified by being extremely low resolution and by being a color scale of just 4 shades, going from white to black with 2 shades of gray in between. But when we get into more realistic images, a lot of the idea behind what we did with this M here is still true. It still holds. It's just much, much larger matrices and a much larger range of numbers used for each entry. So in this case, we use this scale here to tell us how to code the 4 different shades as numbers. And we can see that the M that we have in our first image shows up in the matrix as an M composed of 2's, which is dark gray, on a background of 0's because 0 is white. So this is the matrix encoding of this same image. We can also see that this matrix of all 1's gets added to our image matrix, creating a matrix that also has an M shape. In this case, the M is composed of 3's on a background of 1's. And that would translate to an M that's black because 3 corresponds to the color black on a light gray background. So the addition of a matrix of all 1's caused the image to be darkened. Naturally, you can imagine that subtracting a matrix of all 1's would cause an image to be lightened. Now, our color scale is so limited that we can only subtract a matrix of all 1's if we don't have any 0's in the first place. So we could back this one up, right? From this image we have here, we could certainly back up to the lighter image by subtracting that matrix of all 1's. A somewhat less obvious image transformation is taking the image negative. And in this case, we're starting with a T that is dark gray. So a T made of 2's on a background of light gray. So our background is all 1's. And the way that we create an image negative is that we start with a matrix in which each entry is 3. So we're taking our darkest color. And that is this matrix here of all 3's. We're going to start with this regardless of what our image looks like. When we subtract off our image matrix, we can see what happens. This first entry here is 3 minus 2, which gives me 1. Now everywhere that I have a 2 in my image matrix, I'm going to end up with a 1, so I can see that I get a T shape made of 1s. If I could fit them all in here. Now I'm going to look at the other entries where I have a 3 in the original and a 1 in my image. 3 minus 1 gets me 2. So everywhere that I had a 1 in my image matrix, I now get a 2. And I can see that the result is a light gray T on a dark gray background. That's the exact reverse of what we started with. So this trick works for any image negative in a strictly black and white. It would certainly still work even if we had a much larger scale of gray colors in between. We would just start with our darkest color and subtract off our image. And of course, these small examples barely scratch the surface of things you can do to edit images, but if you ever play around with photo imaging software like Photoshop or something, just know that in the background there's a whole bunch of matrix arithmetic going on that you might not be aware of.